Hey, what's up, guys? This is Chung. So today, 1728, cat and mouse, number two. I think this is a very interesting problem. So a game is played by a cat and mouse named Cat and Mouse, and then there's a grid size. There's a 2D board here, and on this 2D grid here, they're like walls, they're like floors, they're like a cat, a mouse, and a foot. So here are the description. So C means cat, M means mouse, so on and so forth. And mouse and cat play according to the following rules. So mouse and cat, they will move in turns, where mouse moves first. And during each move, right? Cat and mouse can jump in one of the four directions. Basically, it's four directions, and they can jump and they cannot jump over the wall or outside of the grid. So which means that if there's a wall, right? And if say that this is a cat, the cat, and here there's a wall here. So there are some like play floor the cat can jump. But let's say there's another floor next to the floor, even though the cat can jump to here, but he can't because there's a wall here. So here is not like a valid move. And then we have like a cat jump and mouse jump, which represents the maximum length the two players can jump. And so the cat and mouse, they don't have to be jump to the maximum jump every time. They can jump any length. And also staying in the same position is allowed, which means that when this player moves, he doesn't have to move, right? He can just stay there. And mouse can jump over cat. So this thing means that if cat is here, right, and let's say the mouse is here, he can jump over cat until uh to to here, right? So this is a valid jump. And here are the exit condition, right? If the cat and the mouse ended up at the same position, then cat wins. And if the cat reaches the foot first, then cat wins. And if the mouse reaches the foot first, mouse wins. And if the game cannot be finished within 1,000 turns, cat wins, right? So, and here are some examples, right? So, and in this case, right, uh, mouse uh, mouse will win because mouse can jump two, but cat can only jump to one. That's why the cat, basically the mouse can get to the foot first without being caught by the cat. And here are some more examples, right? There are like some true, there are some false, and yeah. So that's the description. It's kind of a little bit long, and the row and the columns they're within 8. Yep. So so for this problem, since there are two players, right, and one of the each of them takes turn to make the move. So this is obviously a game theory problem, which means that with this game theory problem, it's you're always assuming, right? You're always assuming the two players will play optimally, and and then you just need to find a way that who can win in the end. Mm, and the common template for this kind of game theory is that we always use a DP, right? So it's like basically it's a top-down DP, and two players will both assuming will only try to play the way uh, he can win as much as possible, right? So in this case, the let's define like a DP function here, and then we can I'll explain the different strategies while we're coding. right? So we have a DP here, and then we have a cat, we have a mouse, and then we have a moves, okay, right? And then we're gonna have like the memorization for Python, right? So that's that, right? So in the end, this thing will basically will return either true or false. And since this asking you to return the true if mouse wins, right, and false if it cannot win. So basically, this thing will just return that. So if the DP return true, it means that the mouse will win. Otherwise, the cat will win, right? Right. So and then we'll also need to so this cat and mouse is a location, the current location for the cat and mouse, and the moves is the current total movement. So before implementing the DP function, we need to create some global variables, right? As always. So this thing is n and 0. Uh, I have a cat, right? Equals to the mouse, equals to the food, right? Equals to none. So because I'm going to populate these three variables that I'll be using later on. So we have a I in range of m for j in range n. If the grade ij equal to c, right? And then the cat will be the I and j. Similarly for the mouse and food. This is the mouse. This is also mouse. And then for the food, right? So this is food. This is food. So now we have this kind of three variables that we'll be using later on, and then of course the directions, right? Uh, mm, yeah, so that's that. And then here in the end, we simply return the DP, right? So with the cat starting position, the mouse starting location, and the moves is 0. So now it's time to implement this DP, right? Mm, to start with, right? So let's try to find the exit point first. So what is the exit point for this kind of for each of the DP? That that's when we need to go back to the ending weights here, right? So first one, if the cat has uh, has caught the mouse, then mouse loses, which means we need to return false. And same thing, if the cat reached the food first, then we also need to return false. Second one, right? If the last one is the if the moves uh, has reached a certain level. So, but let's do a 1000 here, but we need to change this one later on because 1000 will lead to a TLE. But let's just write it here, right? So and then we also need to return false. And then and if the mouse equals to food, right? Then we return true. So all the three cases will lead to a win for the cat, and only this one, only the last one will make the mouse win the game. Okay, so that's that. Now for the scenario part, since cat and mouse has different different goal, right? That's why we have to handle them separately. So and instead of making another flag here, we can simply use the moves here to help us to determine who is the current player, right? Simply if the moves it's even, right? And then it's it's a mouse turn, right? So for the mouse turn, right? So what the mouse would just do this. So directions. For each of the directions, the mouse will make the jumps, right? The jump gonna be in range of the 0 to mouse jump +1. That's the on each direction the all the scenarios for the mouse. So let's say the new I equals to the mouse up 0 plus D0, right? And then times jump. Similar for the new J here. So we have a J 1, 1, and 1, right? It's here. And here it comes a little bit the tricky part. Actually, it's not. I mean, so for actually, generally speaking, for game theory, right? Since each player will play optimally, and this DP, right? DP will return either true or false based on different player, based on who is the current player. So let's say the mouse is the current player. So what's going to be the optimal uh, solution for mouse? Basically, I mean, if there is any scenario that can lead to to a win, right? Basically, if there's any scenario the DP can return a true, it means that the mouse will definitely go to that direction. I mean, will definitely go to that scenario, which means that as long as there is a scenario that can give mouse a win, the mouse will take that direction. So which means, what does it mean? It means that, as long as of course, we need to do some sanity check here, right? And new j, so n, and grade, right? I and new I and new j is not equal to the wall, right? Then basically this is what I mean. If the DP, right? If the DP dot cat and the mouse is the new mouse, right? So then we have a new location here, and then moves +1, and then here we just return will return true here. In the end, right? So later on here if nothing can lead to a win for a mouse, then that's the time this DP will return false. As long as there's one scenario that can give mouse a win, the mouse will assume that basically will announce, okay, I can win the game. But if none of the scenarios works, right, and then the mouse has no options but to admit his failure. And one more thing to be noticed here that, since we cannot go over to the wall, so what does it mean? It means that if else, we need to break. So this is for actually this is for both of the cases, right? Because if the current one is already outside of the borders, there's no need to keep going because this jump will just keep increasing. So as long as we have reached the border, there's no need to continue. Same thing for the wall, right? Since we cannot go over the wall, once we have reached the wall, there's no need to continue either. Yep, and basically that's the logic for the mouse. And so let's see how can we implement the cat's logic, right? So, so this up until this part, they're almost the same. I'll just copy and paste here. The only difference is that we have a cat jumps, right? And yeah. So for the cat, how will cat play optimally? Mm, so similar, right? Similarly, like the mouse, but cat will think it in a different way. Since this one, since mouse will return true as long as there's any scenarios that can give cat can give mouse a win. That's it when it will stop. Similarly for the cat, as long as there's a scenario can make the mouse lose, right? And the cat will will definitely take that scenario. So which means that, if there's a scenario that can return a false, right? So here we have a new I, new j, and then we have a mouse dot moves +1. If there's a scenario that can make a mouse loose, right? The cat will definitely go to that direction. Basically, then the cat can say that, okay, this scenario the mouse will lose, and then I will just take scenario, and then I can announce that, okay, so for this DP you need to return false because the mouse will definitely lose in this case. Similarly, it also needs to break here, right? And but But if there's no scenario, the cat can make the mouse loose, then similarly as the above one, so the cat has to admit uh, the mouse can win. Yeah, I think that's the a little bit tricky part to basically to stop and to return, right? So you have to think about it really carefully. And now, that's the basic scenarios, right? And let's revisit some of the constraints here. So mouse can jump over cat. So which means that, the mouse can jump over cat. I believe here is fine because, maybe you maybe you're thinking that maybe we need to add a few more conditions here, like if the new I and new j does not equal to cat, then we can continue, right? I mean, because if the new I new j is a cat, basically the mouse is kind of equivalent to to suicide, right? I mean, and this DP will definitely doesn't make sense. But actually we don't need to worry about that here because we have all this kind of exit conditions here. Let's say the mouse jump directly to the cat, and then that DP recursion function would definitely return false because of this because of the first if condition. And then basically the mouse will just skip this DP because it's returning false, and it will try the other scenarios. So that one can be covered by all this kind of if conditions. And what else? Um, so it's saying that no mouse can jump over cat, but cat so this one is implying that cat cannot jump over mouse, right? So, mm, but I think that constraint is a little bit weird because actually we don't need to worry about that one either because let's say there's a cat, right? And there's like a mouse here, and there are like some like other floors after that, Since we have this kind of if condition here, for the cat, right? So as long as a cat, so the cat cannot jump over because it's kind of obvious because before jumping over to the mouse, the cat would have already caught the mouse. So if for some new I and new j is the mouse, right? It's a mouse, then the cat can catch that mouse, and then here it will return false, and that's basically will just simply exit from here. And that's why this if condition can just cover that like implying condition here. And yeah, I think seems like this logic can cover all the constraints and the conditions here. Yeah, but if you run this code like right now, it will TLE because of this 1000 moves here. So the last problem is how can we reduce this 1000 number here. And this is going to be a little bit tricky. And I think first question is that why we have this kind of 1000 turns limits? Mm, this is because, in some conditions, if both cat and the mouse play optimally, this game will never end. And why is that? Uh, Let me try to give you an example here. So let's say we have like a 2 by 8 board, and we have a dot dot C dot 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 and food. And on the second line here, let's say we have a dot, we have a mouse here. There's a dot dot there, and then there's a wall. Dot dot dot. So for example, this is the grid here, and so let's say the cat jump is 1, right? And the mouse jump is, I don't know, maybe 7 or 8. It doesn't really matter. Okay. So if the mouse moves, so what's his option here? He cannot go up because if he go up, the cat can just can catch him. He cannot go. He can go left and right, right? But he can only go as much as far as to here because there's a wall ahead of him. But if he go here, right, and the cat is basically it's waiting here. The cat doesn't need to move, and the mouse cannot go up because if he go up, the cat will catch him. So basically, so for this kind of scenario, the cat cannot reach the food before mouse, but the cat can make the mouse never reach the food because let's say if the cat is trying to move forward and to the food, right? Let's say if the cat moves to here, 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 and here, and then the mouse can simply once the cat has moved to this location here, the mouse can go up, and then he can just the next move he can just reach the food directly because the mouse can jump to up to 8, right? So that so for this one, cat can never reach the food first, but he can just hanging around here to make sure mouse will never be able to reach the food. Because like I said, let's say the mouse move here, the cat can simply stay here. What if the mouse move it to here, right? So if the mouse move to here, and then the mouse maybe can go up and then go right to reach the food. But if that's the case, the cat can also move one step to the left. And in this case, the mouse cannot go up because the cat will catch him. And then what can mouse do? Maybe he can go back to here. He can go back to here, try to go up, and then the cat can simply just move back to here. So basically, it's like an infinite loop here, right? So the mouse can move either left or right, and the cat can also move either one to the left or one to the right to always make sure the mouse can never go up. So, yep, and that's the scenario. And now the question is that what's going to be the proper movement so that we can make sure this game will never be finished. Um, there are like some theories that's people saying that also in the comment uh, areas. So for this part, I'm not 100% confident of the proofs, but I'll just give you what I know here. So this game actually, one of the theories that the you can think of this come try to get this number by thinking of the worst scenario, which means that let's say there's like a 8 by 8, 8 by 8, not 8 by 8, but there's like a grid here, right? Let's say they're all like floors, and the the cat is here, and the mouse is here, and both cat and mouse can only move one jump at a time. So in this case, the mouse will basically move either to right or down, but the cat maybe I think it will try to follow him, right? And then it will try to follow him until the mouse will reach the end. Let's say the food it's right here, it's on the bottom right corner. So in this case, I mean so what's the total movements that takes? It's gonna be m times n uh, times 2 because the mouse will make m times n times, and the cat will also move m times n times. That's why the total movement for this one is m times n times 2. And this is going to be the worst, I mean the worst scenario or the corner case that the game will finish. So and then this leads to like conclusion, right? So if the movement has reached the m times n times 2, then the game we need to return false because by the time the moves have has reached these numbers, it means that there must be some a circle within the movement. That's when we don't need to continue. We can simply return false. And this is based on like the assumption that the mouse or the cat. I think the mouse doesn't need to go back to the position he has previously visited. Mm, he will always try to go to the food, right? As long as he won't get caught. But for that part, I'm not 100% confident, and I don't know how to prove that. So basically, that's the that's the pruning part. And okay, so let's try to run the code here. Yeah, false. Uh, food. Okay, did I make a mistake? Hmm. Cat. So here equals to true or false. This looks right. Uh, oh, here. Yeah. So since I copy and paste, maybe I shouldn't have never have copy and pasted. So here should be cat, not the mouse. So accept it, submit. Yeah, so it passed. And yeah, so for the time complexity, right? So I mean for this kind of top-down DP here, so how many state we have? So for the cat, there could be so for this one, there could be m times n possibilities, right? Because that's a m by n grid here. So we have a m times n. Same thing for the mouse, right? That's going to be another times m times n. And then that's going to, and the second one, the last one is the movement. since the movement is 2 times m times n, so actually, so the time complexity will be the m times n cube, cube of m times n. That's going to be time complexity. Since because for here, right, the uh, actually it's a little bit more than that because here, so this one, the 4 directions, this is a constant, but for the jumps here, right? So the jumps is it's gonna be so what's the range for the jumps? Yeah, so the jump is also like another time, another either m or n. That's why actually so here we also need to add another level of the mm, another like either a m or n here because we have another for loop here. So it should be m times n and then times like jumps, right? Maybe another m or n jumps. Okay, yeah, I think that should be the accurate time complexity. Okay, so yeah, that's pretty much for this problem. You know, the so to recap, right? So we start by identifying this problem is like a game theory problem, and for any game theory problems, you know, we have to uh, uh, basically handle this each player differently. But you know, for some game theory problems, you don't have to do a if else here because let's say for some theory problems, you know, the let's say there are like 2 players that can take the stones, right? Uh, uh, in turns. Basically, you know, both of them will have the same winning conditions, so that you know here we can simply use uh, we can use the same logic to handle both of the players. But for this problem, you know, the since cat and the mouse have a different winning conditions and has a different movement, that's why you know we have to separate the logic. And yeah, and then yeah, and other than that is about this like about this limits, right? Regarding when the game should end. Like I said, so for this one, I'm not 100% confident or uh, or 100% sure how to explain this one. But anyway, this one it just worked. And yeah, if anyone of you knows the a better explanation or better uh, proof for this one, I'll be more than happy to know that. Mm, cool. And I think I'll stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.